Okay, thank you. Okay, so good afternoon, good evening, good morning, good night, wherever you are. We're going to talk today about transactions. And as you probably noticed, the reading material for today is a little bit more tutorial in nature. We're not studying a particular system and see how a set of IDs are implemented in that set of in that system. Instead, what we're going to be doing is talking about just the concept of transactions, because it shows up in the next two papers that we'll be studying. And those two papers have quite a lot of material in them, and assume that you're familiar with transactions, and in particular that you're familiar with the two core ideas that we'll see in today's lecture, namely two-phase locking and two-phase commit. And sometimes they are abbreviated as 2PC for two-phase commit and 2PL for two-phase locking. One point of confusion: the two terms really don't have to do much. Are really not much related. They happen to have both the word, two words, two-phase in it, but they solve completely different problems. They happen to also show up typically in the context of transactions. But they're even outside of transactions, they are good ideas or worthwhile ideas. And so don't let yourself confused by the fact that they both have two-phase in it. They're pretty unrelated. Okay, so I'm just going to dive in a little bit and start talking about transactions in general. And the reason that we're going to care about transactions a lot is that we want to be able to do cross-machine operations. So the problem that we're going to try to tackle in this lecture, as well as in the two upcoming papers, is cross-machine atomic ops. And so, for example, just to make it a little bit concrete, let's say we have a client. We have a sharded key value server. So some of the keys are on key value server 1, some are on key value server 2. And so the keys are split across them. So for example, maybe key value 1 has X, key value 2 has Y. And we basically want to do atomic operation across those two keys. And the easy way, the classic example in the context of transactions is always doing a transfer. So let's say the client wants to do a transfer from X to Y. So here's our client, and it's going to do basically a put to X to maybe add or subtract from the account. So let's do X minus 1, and then the client is going to do a put of Y plus 1. Transferring basically $1 from the account X to the account Y. And our goal is basically going to be, we want atomicity with respect to failures and concurrency. So even if for KV1, the first key value server fails after the put, then we're more likely to arrange it that basically the transfer didn't happen at all. So generally, the semantics that we're looking for is that both operations happen or neither one of them happens. And so similarly, from a concurrency perspective, if another client is running and also tries to inspect these accounts, then what we would like to be the case is that both puts show up atomically. And so another transaction cannot observe an intermediate result, so where an intermediate result is, for example, the money is deducted from X, but hasn't been added to Y yet. And so these are the type of things we want to do. And it's quite common in distributed systems, that you would like to do operation across shards. So that's sort of the context of what we'd like to do. And the general plan for doing this comes actually from the database community. And this general plan is transactions. And what we like to do is basically group these operations. So, for example, in the case of the transfer, the two put operations into a single transaction. And we like then the property that this transaction executes atomically. And so, typically, this requires some programmer annotations. So, begin transaction to indicate that the client wants to do the start of a transaction. Maybe then, the operations like at x. I guess I did x -1, and then at y +1, and then you have to indicate like when the transaction actually is completed. And so typically we come to make it a commit, and so the semantics that we're looking for is that these operations are executed atomically with respect to concurrency and with respect to failure. And just to make it a little bit more exciting, let's look at a second transaction so that we can look at some case studies about how transactions actually interact. We might have a second transaction, begin X, which reads actually these accounts. So T1 gets X, and then T2 gets Y, and then print T1, T2, and then end or commit. So we have a second transaction that basically reads the accounts X and Y and then prints the values. And one reason that we have two transactions is so that we can look from the concurrency perspective how these transactions are actually ordered and what are a legal outcome and what are illegal outcomes. Now, transactions turned out to be a general, almost like a piece of magic. Basically programmers can annotate these begin and end operations, and that takes a whole group of operations together, make them atomic, and just the system will take care of everything. It will take care of the locking, it will take care of the recovery. It's all like the program doesn't have to worry about it. The transactions are a very, very powerful construct, and they're useful in non-distributed systems. If you have a single database machine or multi-core database machine and clients are submitting transactions to it, then the transaction systems will execute these transactions in as much as concurrently as possible, but also even if the machine fails and comes back up, you can actually expect the results to be there. And our focus, of course, is going to be on distributed transactions. Of the ones that I had on the previous slide, namely one, for example, across shards, which is sort of a common case in data centers. The typical API of a transaction also has one more operation that I didn't list here, and that is abort. So the two transactions that I'm showing here are both committing, but you could easily have a transaction that decides to abort. For example, you might discover that, for example, transaction T1 might check that X has sufficient money in it in the account, and if the account doesn't have sufficient money, instead of calling commit, it would call abort, and at that point the transaction would be canceled. And even if a transaction aborts, sort of halfway through, and maybe has done some put operations, still the semantic should be that none of those put operations actually happened. So in all cases where it's abort or commit, either all of them happen or none of them happen, never a partial result. Abort also might be called by the transaction system itself. So for example, as we'll see later, if there's a deadlock between two transactions, then the transaction system actually can abort one of the transactions so that the other transaction can continue and maybe retry later the transaction that was aborted. Okay, so this is sort of the primitives: begin, transaction, commit, and abort. Those are the three key interface operations. And then the semantics of transactions are typically summarized by a single word, namely ACID. And that stands for like 4 key properties of transactions. One, it's atomic. And here really atomic refers to the case where we have 2 transactions running. And if one transaction does multiple put operations or multiple add operations, all those results will be all visible to the other transaction, or none of them will be visible. So that's one aspect. Sorry. I said this is wrong. So atomic actually means to the crash recovery case. If a transaction actually executes multiple put operations, the transaction crashes halfway. The rule is that all the writes are visible, all the writes are on a stable storage, or none of them. This is the atomics with respect to crash recovery. The C stands for consistent, which is something we're mostly not going to talk about. It's more related to databases. It's often the case that databases have internal invariants, like referential integrity is one of them, and the transaction is supposed to maintain that consistency. And so no internal consistencies. This is going to be less of a topic for us today. And 3 is isolated. The I stands for isolated. And isolated was the what I just said earlier incorrectly. Isolated actually refers to the case of we're running 2 transactions, and they shouldn't observe intermediate results from each other. So again, all the writes are applied, all or nothing with respect to the visibility to another transaction. And then finally, the D stands for durable, meaning that if the transaction commits, then the results are written to a stable storage, so that if the system crashes, comes back up later, the latest writes or the latest transactions, the latest committed transactions are actually recorded on stable storage. Any questions about sort of the quick introduction to transactions? Okay, so I'm going to talk basically about 2 topics quite a bit, namely the A part of the transactions and the I part of transactions. I'm going to start with the I part and talk a little bit about what actually correct isolation means. So basically what we're looking for is a definition for a correct execution of multiple transactions, concurrent transactions. And the typical definition, or the gold standard in the database literature, is called serializable. Or serializability. And what that means is that if you have 2 transactions or many transactions and they execute concurrently, then the outcome has to be some serial order. So either T1 executes before T2, or T2 executes before T1, but there's some serial order. And the serial order has to produce the same outcome as the concurrent execution. So if you run 2 transactions concurrently, they produce some outcome. That outcome is only valid or legal or correct if it could have been the result of a serial execution. So just to make it concrete with our example, let's say in the account case, X starts out as being 10, Y starts out as being 10. We run these 2 transactions that we had earlier on the board. Just to quickly remind you what the 2 transactions are. And one basically moves one between 2 accounts, and the other one prints the result of the 2. So if we think a little bit about it, if T1 goes first, then the outcome is going to be 9, 10. And the print statement is going to be and the print statement, actually, did I say 9, 10? Oh, sorry, 9, 11. That's why I got confused. And the print statement is also going to say X was the one that was subtracted, so 9, 11. So we get a string 9, 11 out, and the two values of the counts are 9 and 11. If T2 goes first, then the outcome is 10, 10, because no money has moved yet. And then T1 goes, and so that's the possible outcome. Right, so that was the two legal outcomes of the two transactions that were actually, if we executed the two transactions concurrently, and the system guarantees serializability. Now, you notice that serializability has probably a lot of flavor of like the terminology that we used before, namely linearizability. The key difference between serializability and linearizability is that in linearizability, there's a real-time component that if a transaction T2 starts after a T1 ends, then T2 has to show up later in the total order, in the serial order. In serializability, that is not required. So even if a transaction started, wall clock time a little bit later than another transaction stopped or finished, the system is still allowed to reorder it. So serializability in some ways is a little bit weaker than linearizability. Nevertheless, serializability is a very convenient programming paradigm, right? Because from a programming perspective, you can always think about transactions executed in some serial order, and you don't have to consider all kinds of interleavings. Okay, so even though serializability is slightly weaker than linearizability, it actually disallows a whole bunch of problematic cases. So let me talk a little bit about that just to make clear what actually serializability means and what sort of executions the transaction system actually has to forbid. Let's two cases, like here we have the first transaction, we have the second transaction running. So T1 runs T2, and one outcome that we could have is like one possible execution that might happen is if we don't do something special, T1 gets X. Here the transfer happens, so the updates to X and Y happen. And then T2 does the get of Y, and is this a legal, or is this a serializable execution? That's the sort of question that we have to ask. And what is the answer to that one?
This is not serializable.
Yeah, and because the outcome, if we write down what the outcome is, correct, then the outcome is going to be 9, 11 here. And this is going to write down 10, 11, right?
I think so.
And if we go back, to our previous slides, that is not one of the two legal outcomes, correct? So this is not good. So when we think about the implementation of a transaction system, it has to be the case that it forbids this particular execution schedule. And there's a similar version. Our transactions on these two examples are not so complicated, so there are not that many interleavings that you can consider and that could go wrong. But there's at least one other one that can result in not an incorrect outcome, which is we do the put X first. So here we go. Then we actually print the two gets. So get X, get Y. And we do the put of Y. And is this a serializable execution? Is this an execution that we should be forbidden by the serializable transaction system, or is it an okay execution?
It should be forbidden.
Yeah, it should be forbidden, correct, because it has an outcome that could not have happened if we executed T1 first followed by T2, or T2 first followed by T1, right? Okay, so what we clearly see is that serializability excludes executions just in order to actually make it easier for programmers to think about actually what a database does. And there are two broad approaches to forbidding executions. And these approaches, the approach to forbidding is called concurrency control. In the first approach, or the first category of solutions, is what is called pessimistic solutions. And the pessimistic solutions basically involve locks. So the idea is that, like, when the transaction runs or starts, it requires the necessary locks to maintain serializability, and only releases the locks so that when it's guaranteed that the executions will result in a serializable execution. So that's the one approach, and we're going to talk a little bit more about it in a second. The second approach is optimistic. And in the optimistic approach, there's basically no locks. And in the optimistic approach, you just assume things are going to work out. And basically, when you get to the commit point, the transaction system sort of asks itself the question, well, given the operation I've done in the past, could that be the result of a linearizable execution? Or could that be the result of a serializable execution? And if so, things are fine, and no problem at all. Then we're good. If it is the result doesn't correspond to a serializable execution, then we're basically just abort. And maybe and then we'll retry probably. So we'll see. I'm not going to talk much about optimistic concurrency control right now, but next week or 2 weeks from now, actually, we're reading the farm paper, and we'll see an optimistic a transaction system, distributed transaction system of the type that we're considering, that uses an optimistic concurrency control approach. But the focus for today is going to be on pessimistic. And one, sort of the flip way that these two approaches are described in the literature often is that sort of pessimistic is, you ask for permission first, and then you do your operations. And the optimistic is sort of the other way around. You just go ahead and you do your operations, and if it turns out to be wrong, you just apologize later. And so that's the sort of the analogy, if you will, sort of between the two different approaches. And now within each approach, whether it's a pessimistic or an optimistic, there are many different concurrency control plans, to either increase concurrency or provide weaker consistency with more concurrency. And so there's a huge literature. And I'm just going to talk about one particular approach, which is very popular, particularly if you want to achieve serializability. It turns out that although I said like serializability is the gold standard for databases, it's often the case that databases offer multiple degrees of isolation. So as a programmer, you can sort of pick the degree of isolation that you like. And the reason that you may want to pick a weaker degree of isolation is so that you can get more concurrency. Now, we're going to just stick to sort of the gold standard of concurrency, which is namely serializability. And if you do serializability, then a common approach is two-phase locking. And in two-phase locking, they're basically sort of a lock per record. That's the starting point for database record. And in our little example, that would be sort of a lock per variable, a lock for X and a lock for Y. And there's basically two rules. One, a transaction acquires a lock before using. And so the idea is before you can read or write to X or Y, you first have to obtain the lock, and the transaction system will do this for you. And two, the T holds a lock. Once you acquire it, you're not allowed to release it until commit or abort, whatever is the end of the transaction. Correct? And so in our particular case, if we have like T1 running and we have T2 running, and T1 locks X first, and then lock Y, and it has to maintain those locks until it actually reaches its commit points. So if T2 runs at the same time, or roughly at the same time, if T2 starts a little bit later and tries to grab the lock in X, T1 will have it if T2 started a little bit later. And at that point, basically T2 has to wait. That's sort of standard locking protocol. And the basic idea of two-phase locking is that it's sort of a refinement or an improvement over this simple locking scheme that is described in the document, and which sometimes is called simple locking or strict locking, where basically at the beginning of the transaction, you grab all the locks you need for the whole transaction, you hold them until the end, and then you release them. And two-phase locking is a little bit more fine-grained in that even if the transactions might and then they don't require the locks immediately all at the same time at the beginning. And instead, they acquire the locks incrementally as the transaction runs, which allows certain concurrency patterns that are disallowed by strict locking. Now, the first rule seems pretty clear, why you need it. The second rule might be maybe less obvious, and so it's probably a good idea to actually sort of see what goes wrong if you did not maintain the second rule. And so let's say talk a little bit about until commit. And so here we have our two transactions, T1 and T2, the transfer and the print statement. And so let's say, here we do our put of X. And so that means before the put of X, the transaction system locks X. And let's say that we're not following the two-phase locking rule, and we actually release the lock X right after the put, because we're done with it. Actually, it doesn't show up in transaction T1 anymore. There will be a later put, but that's the put to Y. And let's assume that before actually we get to the locking of Y, T2 runs, and actually T2, basically the whole, the two gets, the get of X and the get of Y run. And so since, T1 released the lock on X, it can get the lock on X. Since T1 hasn't gotten to the put yet, it can also get the lock on Y. And so, print X and Y, and we're set. And then release the locks. So would this be a serializable execution?
No, it's the same as before.
Yeah, it's exactly the same as before, correct? Because basically the print statements like here, they sort of slipped in between the two, the put and the get and the Y, okay? Between the two puts of the X and the Y. And we already concluded earlier that is not a serializable conclusion, that's a serializable execution. So this is wrong. And so this is an example of demonstrating that if you release the lock too early, in this case, T1 released the X too early, you're not going to get a serializable execution. And one way to think of that basically is that whenever there's sort of an intersection between two lock sets, so T1 has a lock set of X and Y, T2 has a lock set of X and Y2, it is important that during these two transactions get ordered in a particular way, and that means that if the lock sets intersect, we have to ensure some total ordering, and that means that we actually have to hold the locks, to the end until the commit point, so that no intermediate results of the transaction are actually visible to other transactions. And we release the locks before the commit point, we might actually make a result visible, even though, maybe later the transaction even aborted, right? And then the whole change will go away. So this is the reason why, locks must be held to the end. Now, an obvious problem that many of you asked about in two-phase locking is, isn't there a chance of deadlock? Because you're requiring the locks as sort of the transactions execute. And so and this is absolutely the case. And so, for example, let's modify T2 slightly. So T2 used to be, T1, gets X. Instead, we're going to do it in the opposite order. We're first going to get Y, and T2 gets X, and we keep T1 the same, right? So T1 actually still does first the put to X and then the put to Y. And so now we can easily get into trouble. So this is T2 prime, and this is just the ordinary T1 that we already had. It does a put of X. Before doing the put of X, it needs to get the lock on X, so L locks X. Now let's say that the ordering works out as follows. The same time T2 prime runs, it does a get of Y. So that means it got the lock on Y. And now you can easily see what goes wrong here. Now T1 is going to do a put of Y, or it wants to do a put of Y. So it needs to get the lock on Y, but it can't get it because T2 prime actually has the lock, so it has to wait here. That's the block. The same thing is going to happen, of course, on the other side. When before doing the get of X, T2 needs to get the lock of X, and it can't get the lock of X because T1 has it, and so this has to wait too. And now we have T1 waiting on T2 prime, and we have T2 prime waiting on T1. We basically have a deadlock. Now, what is the cool part about transaction systems is that we have this abort operation. And so if the transaction system could detect a deadlock, it could just abort one of the two transactions, let the other one proceed, and hopefully that will actually get to the end and commit, and abort the other one. And then the client or the application can decide what to do with the aborted transaction. It can actually retry it, maybe wait a little bit and then retry it, and in the hope that at that point you're not going to run into a deadlock. And so one way to think a little bit about two-phase locking is that it has a little bit of a sort of an optimistic flavor to it, in the sense that it's not guaranteed that it won't run into problems, but even if it runs into problems, you can always abort and then recover from that problem. Any questions about this?
So how do you find the deadlock?
That's exactly. I was hoping that somebody was asking that question. So there's sort of two broad approaches that people use. One is not as solid, as you will. One is just basically on a timeout basis. Like if the transactions are running for a long time and then they don't seem to make forward progress, you can just abort one of them. And so this is timeout based. The more systematic sort of way of thinking about it is to construct a wait for graph as the transaction systems are moving. So for example, if T1 runs, so in the wait for graph, the transactions are the nodes. So we can have a node T1, and we make a node T2 when they start, or T2 prime, if you will. And when T1 runs, it gets X, nothing to there. Then it gets to the lock of Y. It can't do it. So we'll make a arrow from T1 to T2 prime to indicate that T1 is waiting for T2 prime. Then at some point, like T2 is running, T2 hits this, T2 prime hits this point where it wants to lock X. It can't do it. So we'll look at like where it's waiting for, who's holding the lock. Well, it's T1, and so we'll put an edge, in the wait for graph from T2 to from T2 prime to T1, and now we see that there's a cycle. And whenever there's a cycle, that means there's a deadlock, right? Because one is waiting on the other, and the other is waiting on the first. And so the transaction system can sort of construct these graphs on the fly, detect when there's a cycle in the graph, and then, for example, either abort T1 or abort T2 prime. So this is called a wait for graph.
What happens after the abort?
So let's say we abort T2, just for as an experiment. So we're going to kill this guy. So T2 basically, this transaction system is going to arrange, as we'll see in a second, is going to arrange that basically none results of T2 are T2 prime invisible. At that point, the lock is released, right? The abort will force the lock release of the Y because T2 prime is backing out. That means that T1 can get the lock on Y and proceed to finish. The client that called T2 prime is going to learn that the transaction aborted, and for example, it can just choose to rerun it again. Does that all make sense? Okay, so this is sort of the first part. Actually, all I wanted to say about two-phase locking, except I wanted to address the sort of homework assignment again, which is like, in what situations does two-phase locking allow for more concurrency than strict locking, right? Where strict locking was the protocol where a transaction acquires all the locks in advance. And this requires that the programmer, or like the beginning of the transaction, basically declares which locks that transaction actually needs. And so they're slightly undesirable, like less programmer friendly, but it has the advantage that you don't actually you can run into these. You don't have to abort a transaction at the end in the case you run into a deadlock. So two-phase locking allows for more concurrency in principle, or it should allow for more concurrency than the strict locking or the simple locking scheme. And so I would like to do is a quick breakout room for a couple of minutes, like 5 minutes again, and convince yourself or construct a case where simple locking would disallow some concurrency that two-phase locking was actually able to exploit.
Cool. All right, let's do breakout rooms. Okay, see you in 5 minutes.
We can't hear you.
I think you're muted.
I have a question about one of the previous slides that you're talking about.
Yeah, hold on a sec. Let me double check if everybody can hear me now.
Yep.
Yes.
Okay, good. Go ahead.
On one of your previous, or I guess this is just a general question, but is the lock point always the same as the commit point? Or is it possible to start relinquishing locks before your commit point?
Okay, this is a very good question. So it depends. So if you only do exclusive locking, as we've done so far, at least in my examples, then the commit point is similar to the lock point is similar to the commit point and the abort point. If you have read-write locking, so locks that allow both read locks and write locks, then it's possible to release read locks earlier with some restrictions.
Thank you.
Okay, so can somebody give me one example of where two-phase locking allows for more concurrency than simple locking? Just to make sure that we're all on the same page.
The audit function example, like you can release the lock as soon as you read this person's amount. Like you don't have to wait until you read everyone's.
This is an example of exploiting the read locks, if you have read locks. Yeah. Any other examples?
If you have a transaction where there's like a condition that only rarely is true, and you read a piece of data when it's true. So at the beginning, you don't need to acquire the lock for that, only when you actually need to read it.
Yep, that's a great example. I personally like that example a lot. That's a great one. Good. Okay, good. So let's move on basically then to the second topic of this lecture, which is two-phase commit. And this is really dealing with crashes. Switch back to blue. I don't know why, but
We can't see the slides either yet.
oh, let me fix that. Hold on. Share screen. Stop to share. How about now?
All good.
It's good.
Good. Thank you. Okay, so two-phase commit, or 2PC, as it's popularly called. Again, this is a very well-known, popular protocol. I'm going to talk about the base, sort of simple, straightforward, or the most common version of the protocol. There are all kinds of variations of it, but they all sort of have the same underlying idea. And so again, typically in two-phase protocol, and I'm going to do it in the context of the transfer transaction. So a client that actually wants to do a transfer, basically submits the transfer transaction to the transaction system, and the person or the machine that sort of receives that transaction is called the coordinator. And that machine is in charge of running the transaction through the transaction system. And so the coordinator will talk, in our case, to two different machines, A and B, where A holds X and B holds Y. And basically, the one way that this typically goes is that the coordinator first sort of does the whole transaction, but in a tentative way. So the put X, results in a message to A, locking A, modifying A, put X, except, the put is not actually visible yet in the database. What is done, it is put in a log, very much like in sort of in the Francipani style, where we have a write-ahead log. All the operations that we at some point want to materialize in the database itself, we first put in the log until later, in this particular case, until we hit commit, and then we actually will install everything in the database. So we'll do the put, we do a second put, to Y. And that the same thing happens there, we get a lock on Y. Okay, so this should have been lock on X. And we'll do a put on Y. And again, we're going to not actually, really put the value in the database. We're usually going to log things. So we're log Y, and here we're log X. Okay. And now the coordinator has done two, the transactions, the two of the main operations, and now it's ready to commit. And here's where the two-phase part comes in. And so the coordinator will send a prepare message. And I'm first going to describe this protocol in the case there's no failures and just everything works out. And just to start sort of the easy case, as you will. Since a prepare message, it sends a prepare message to prepare A, prepare B. And the prepare message, of course, it includes the transaction ID that is actually used for, this transaction. So every transaction has a transaction ID, and all the messages are tagged with the transaction ID, so we always know about which transaction we're talking about. When A and B, receive these prepare messages, they look at their state and see if they indeed can actually execute the transaction. They're holding the lock on X in this case. The X is actually in the log, and so they send back, saying, "Yep, well, I'm ready to commit." So yes, yes, and at this particular point, here's where the crucial sort of step is. The coordinator now knows that basically both A and B are prepared to commit, and then and I have basically promised to commit by actually responding to Y. And at this point, the coordinator commits, and then sends messages again to the A saying commit the transaction TID. Similar message to B, commit TID. And at this particular point, A and B actually perform the operation. So they basically install. At this point, they install, the log version of Y. Here, this participant installs the X, and they release the logs. So release of Y, and here the release of X. And they respond back, to the coordinator saying, like, "Yep, all done." And at that point, the transaction is completely done. And in fact, the coordinator doesn't really have to remember anything anymore about this particular transaction. And also we see later, A and B, need to remember their state a little bit longer until they hear about the next transaction. Okay, so this is the core basic case when there's absolutely no failures. And we see what we actually get the desired outcome, correct? When does the coordinator commit? The coordinator commits only if A and B agree. Okay, and it could be the case that, example, when the coordinator sends a message to B, that B decides, well, I can't really commit. Maybe, so there could be multiple reasons for it. Maybe the B actually is in a situation where there's a deadlock with Y. Or there's no space in the log anymore, or there's not enough money in the account of Y, and so B could respond with a no. Let's say in this So the other possible outcome is, the prepare message can actually send a no back. And in that case, the coordinator gets one yes, from A, a no from B. So both do not agree. And in that case, the coordinator cannot commit the transaction, and then it would actually abort the transaction. And then send abort messages, to A and B, basically, discontinuing the transaction. So that's sort of the two possible outcomes, one in the commit case, one in the abort case. But it is always the case that a transaction only commits, the top level transaction only commits if both of the participants that are involved in the transaction agree to do so. Now, that's sort of the outline of the protocol. So I want to now go through a couple of cases, sort of to understand, what can go wrong, and how two-phase commit arranges that actually still the right thing happens.
Actually, I have a question here. So we said that like B might decide that it needs to abort and sends back a no message. What if it decides it needs to abort after it replied yes? Would that ever be possible?
No, we'll talk about it in a second, but that's absolutely not possible. If you promise to commit, you have to commit.
Or you have to be ready to commit.
No, you have to be ready to commit. Yeah, you don't commit right away. You have to wait until the commit message, of course, but you cannot bail out anymore. So until the prepare, the B can unilaterally abort a transaction. Once a promise yes, it cannot unilaterally abort a transaction anymore.
So is it possible where you're in deadlock, but you can't get out of the deadlock because everyone in that cycle has agreed to prepare a commit?
If everybody agrees to prepare and they can definitely commit, then they will commit. And you're still holding the locks.
Right, but what if you're in deadlock? Because we mentioned before how one of the reasons why you might want to abort is that you're in deadlock.
You would find it out before the prepare. Okay, so you get the locks and why. If you did not succeed in getting the necessary locks for the transaction, then at that point.
Right, thank you.
Okay, so this is exactly the kind of discussion that's going to come up. So I'm going to take the same board and replicate it and consider a bunch of different cases. So here's the same board again. Nothing has changed so far. It's identical. And so let's first, to sort of follow up on this question that was just asked, let's first consider the case where B, is in the prepared state and then crashes like right after. So it is prepared. It pointed back, sent back to the coordinator that it actually is agreeing to go along. And right after it sent actually the prepare message, okay message, it actually crashes. What does that mean? What needs to happen? How we're going to resolve this? Or what is the risk? So basically B crashes.
If B crashes, we need to abort the whole thing, right?
No, we cannot abort anymore, right? Because B already promised that it's going to commit.
We're going to use the log?
Yeah, well, okay, so B is going to crash, and then at some point it's going to come back up, right? And it's going to recover, hopefully. And what state doesn't need to remember a crash crashes?
It needs to remember that are prepared.
Yeah. I need to remember, correct, that it prepared for transaction ID, whatever the TID was. And that is holding the lock on Y. And so when it comes back up, the first thing it has to do is sort of look, saying like, oh, was I in the middle of a participant in a distributed transaction? And if you look at the state, and it will see that it was actually prepared for transaction ID, TID, and it must hold the lock for LLY or the lock for Y before it does anything else. Before talking to anything. Once it is in that state, then it is as if it didn't crash, right? And things are sort of back to normal. And hopefully at some point the coordinator will retry the commit message. The B will get that commit message for this transaction ID, sees that, yeah, I'm indeed prepared, and I hold the lock on Y, and so it just goes along and installs Y and etc. Finishes the transaction. that make sense? So basically, there's a little bit of a refinement here that we actually have to write some stable, some data to stable storage, as part of the transaction, and also as part of two-phase commit. This is one of the reasons that two-phase commit is a little bit expensive, right? Because not only we have to send sort of multiple random messages, but also a participant actually has to write things to stable storage. And as we talked about before, writing to stable storage is quite expensive, right? Like could be easily a couple milliseconds. So let's say it's 1 millisecond. Optimistically, that means basically that we're immediately limited to sort of 1,000 transactions per second, right? And no more. Okay, let's consider another case. And so let me duplicate this slide again. And consider yet another case. Let's say the coordinator crashes, and so here's red again. Oops, cancel. And we got like we got the prepared messages, and the coordinator maybe you set out one commit message and then crashes, like right here. What do we need to arrange to make sure that the whole plan works out?
And so the coordinator needs to store into persistent state what are the commands that were promised to be committed but were not committed yet.
Yeah, so the coordinator is almost the same as sort of it's an analogous to B's case, correct? If we commit a transaction, we need to write to stable storage that we're actually committing the transaction. So we need to write to stable storage, commit TID, so that then when the coordinator comes back up, then it can actually finish the transaction and tell actually the A and B that indeed the transaction is committed, because A and B are waiting, right? A and B said like, yeah, we're happy to go along. And they're just waiting and waiting until actually they hear from the coordinator to decide what's done, because once they decided, once they went along, or once they agreed to go along, they cannot unilaterally anymore bail out, correct? Because let's say they actually both said that they agreed along, then it means that the coordinator, they don't know, the coordinator may have sent a commit message to, for example, A, and A actually has committed the transaction. B hasn't heard yet, maybe the message got delayed, then the coordinator crashed, and at that point, it would be totally wrong for B to abort the transaction. It really has to wait until the coordinator comes back to tell what actually the outcome is of the transaction. Okay. So
the only message that the coordinator is not going to resend is prepare. That one, if it gets doesn't get a yes, it'll just abort.
Yeah, actually, that was the next example. So let's do that. Let me duplicate this board again and talk about that case. So just for fun, let's move it down so we don't lose track. So let's say, the following thing happens. This prepare message never makes it, right? And then the coordinator can unilaterally decide to abort, right? And in fact, you can tell B to abort, and A doesn't really need to know anything about it, because at some point later, we'll come up and can ask the coordinator. If the coordinator doesn't know anything anymore about this transaction, you can just tell IA, oh yeah, no, that's a transaction we aborted because I don't have a commit record anymore, and I was not waiting to inform anybody. So in that case, we can do an abort. And that means that B can release the locks, correct? And B can just proceed, happily trying to do other transactions that might involve Y. Okay.
Sorry, so what will happen if the message to A gets lost, the coordinator aborts, and then B crashes, but then when it comes up, it's going to wait for a commit message from the coordinator, but the transaction has aborted already.
Yeah, or so either there's two cases. Presumably, in the most protocols, actually, B will ping the coordinator because it knows who's the coordinator, and ask it, hey, what's the outcome of that transaction? Okay, so one more case. I want to return to one case that is actually sort of the most interesting case, one of the more tricky cases.
So I just have a brief question.
Yeah, hold on 1 second.
Sorry.
Yeah.
Yeah, so the first question is that, so B, let's say, holds the lock on Y all the way through between putting Y into the log until installing Y to its actual state. So that's, okay. And then the second question, so the locks here are distributed because we're dealing with across servers, or I mean, if Y only exists on the server B, then maybe we don't need distributed locking. So I'm just curious of what the setup is.
Yeah, the setup here is basically that A maintains the locks for all the shards that it has, or for all the variables or all the records that it has, and B maintains all the locks for all the records it has.
Okay, but if we, for example, have Y being on multiple servers, then we need some sort of distributed locking.
Yeah. Like, so this is we're talking about the sharded case, right? Where the accounts are sharded across multiple servers, and only one server has a particular account.
Awesome, thank you.
I'm come back to this later, actually, one more time. So the first thing I wanted to point out is go back to sort of the case where B or A, said yes and then crashes. Correct. Or actually, let me see. Is this the case? No, I want the following case. Sorry. Let me fix this line. So A and B promised their thing, but I want to go back to the case that we already discussed, which is right after the commit point, the coordinator crashes. Correct. And we know, correct, this interval of time from here to there, basically, B cannot unilaterally abort anymore, correct? Because it promised, to go along, and it might have been the case that actually A already did the commit, and so it cannot unilaterally abort anymore. And so there's only one option in this case, and what is that one option?
We just wait.
Yeah, this is unfortunate, but true. The only thing that B can do is wait. And it's still holding the lock on Y, correct? So that means that any other transaction that involves Y, cannot proceed. One has to wait, until the coordinator comes back and announces or re-announces whatever the decision was that actually was the outcome for that particular transaction. And this is one of the sort of the two aspects. This is one of the sort of aspects of two-phase commit that are a bit undesirable, right? Where the protocol might just block until a machine comes back. Does that make sense? So how do people deal with this in practice? Well, it's a little bit unfortunate. But here's where some of our techniques from the past can come to rescue. What could we do with the coordinator to make this scenario unlikely?
So we can make it fault tolerant, like
make it fault tolerant. How could we do it?
well, there are multiple approaches, but we can do it maybe through Raft.
Yeah, run Raft to basically run the coordinator not on a single machine, but basically have a replicated state machine, right, that implements the coordinator, and we use Raft to sort of keep the replicated state machine that implements the coordinator in sync. And then if one of the machines that forms the coordinator fails, hopefully the two others are still there, and so we can still proceed, right? And so it's potentially possible to basically, replicate the coordinator or actually any of the participants too, using Raft. So let me actually put this up a little bit and so talk a little bit as a more. So a couple of discussion points, which is, we could use Raft to make the coordinator fault tolerant or available, if you will. That's really the property we care about. Does that make sense? In fact, if you will see, if you do Lab 4 instead of a project, this is exactly actually what Lab 4 does. Lab 4 actually has a similar scheme where there's a form of two-phase commit that you must implement, and both the master sharder or the master coordinator that rebalances shards across shard servers uses Raft to replicate itself, and actually the shard servers itself also replicate itself using Raft. And so we're many Raft groups running in parallel, and that's sort of the essence of Lab 4. And so this is like typically a way, if you're concerned about like having the system being blocked for a long period of time, one way to do it is basically make the coordinator fault tolerant. So that brings me to something else, which a lot of people asked about. Is Raft, are Raft and two-phase commit sort of similar things? Or could you do two-phase commit with Raft? Or, they have a little bit of a parallel, correct? There's like one thing is called the coordinator, well, Raft is called the leader. We got participants, maybe we can figure about these as followers. So seems to have some similarities. Like, how do we think about it? Like, what's the relationship between Raft and 2PC?
The difference is that in Raft, the coordinator can change essentially.
True.
Otherwise, it's like the single point of failure.
Yep. Good point.
So another difference is that Raft basically depends on the concept of a majority, whereas in two-phase commit, the coordinator needs to get a response from every single other server that is involved in the commit.
Yeah, those are good points. So these are almost sort of like protocol differences, correct? And I was wondering if can we get to a point where like is there a conceptual difference? Like, do they solve the same problem?
Raft is for replicating the same thing. And two-phase commit is when you do the opposite, when you, instead of having one thing, you spread it across different servers, and then you have to deal with the problem.
Exactly. In Raft, all servers do the same thing. They're implementing a replicate state machine, right? And in 2PC, actually all servers operate on different data. The first participant was actually operating on X, and the second participant was operating on Y. So in 2PC, really, solves a completely different problem than Raft. Raft is really all about high availability. And 2PC is really about atomic operations across servers. Or across data that's living on different servers. Does that make sense? So even though like maybe they have some internal techniques that look like very similar, the two protocols are designed for completely different problems and are not directly related. Now it's interesting to see, correct, that we could make a Raft. We can use Raft to make the coordinator more fault tolerant, or the partitions may more highly available, but they basically essentially solve different problems. With that, I actually wanted to end this lecture. I'm happy to entertain more questions. Hopefully this will be very helpful in the next two papers. So the next two papers are both two transaction systems. One from Google, one from Microsoft Research. And the second one uses optimistic transactions. And you will see when you read these papers, there's a lot of machinery. They're pretty complex systems. But hopefully at least some of the parts that will be described, you will sort of now understand because you know what two-phase commit is and you know what two-phase locking is. Okay, with that, I'll end. And everybody who needs to go can go. And anybody who wants to ask questions, please feel free to do so.
Sorry, this might be a little a strange question, but for two-phase locking, it is also about atomic operations, but there it is about one, not across servers, but across one server, and two phases across multiple servers.
Yeah, two-phase locking is relevant too if you have a single machine, like a multi-core machine, and you're implementing a transaction system on a multi-core machine. You will have to lock, the records that are involved in the transaction, and two-phase locking is a perfectly good protocol for doing so. Where two-phase commit is really about distributed systems.
I guess my question was: is two-phase locking, can it be part of two-phase commit?
I'm not sure I know what that means. The way I think about it is they do solve two different problems.
Okay.
It is the case that if you I mean, maybe this is what you mean. It is the case where that there's the coordinator or as part of like the initial setup, like when the initial puts are done by the transaction, that transaction will follow two-phase locking. Here the lock on X is required, the lock on B is required. Or lock on Y is required, and so the transaction does that in a two-phase locking style. It could have done it using strict locking too, but from the two-phase commit point of view, it doesn't really matter. Like at some point, the sort of transaction is tentatively executed, and the two-phase commit is really about reaching agreement that all parties agree to go along.
Yeah, that makes sense. Thank you.
You're welcome.
Is two-phase commit exclusively for like sharded data?
No, actually, it came out, although yes and no. The original sort of two-phase commit came out of the case where like you have different organizations and they need to agree to do something. Like, you book on some a travel website, you book a trip, and another thing, you book a hotel, and you want to sort of commit, to the whole trip if both the hotel website and the travel website agree to go along or sort of commit to the transaction. And that's sort of the setting where sort of the setting that where it came up is really you have different organizations that need to commit to a particular operation, and for the reasons that in that setting, actually, basically people don't really want to use two-phase commit because that would mean that the travel agency website is dependent on the hotel reservation website, and these are from different organizations, and people, the organizations don't really trust each other, and if one goes down, then the transaction can't proceed, and so that seems all bad. So in fact, two-phase commit had a sort of a bit of a negative reputation. Because it's really, one of the original goals of two-phase commit was to solve that problem, but that problem, people don't really want to solve with two-phase commit. However, in the context where like you have a data center, it's a single organization and the database is sharded, two-phase commit is widely popular and typically used.
Awesome, thank you.
You're welcome.
Could you go back to the first failure case that we talked about with two-phase commit, where it fails, B fails after response being prepared? Okay.
Yeah, I think this is this one.
Yeah, I guess.
I think I talked twice about this case, but like, yeah.
Yeah, I guess I was wondering why B needs to persist, or like Y needs to remember that it received prepare. I guess my thinking was when it comes back up, if it receives a commit message from the coordinator, couldn't it just assume that it was prepared? I guess, where does it use that information?
Yeah, well, I mean, it could have aborted, right, before the crash. And B needs to remember what it did.
Okay.
So there's another slight variation of this protocol where where you assume that you always commit, so presumed commit, where the message is slightly different, and there's an optimization that you could consider, and would make sense in some settings. I didn't really talk about that particular protocol, but there's a slight different, sort of variation. There's quite a number of variations for two-phase commit that change in minor ways.
Okay, that makes sense.
Make sense?
Yep, thank you.
Is that it for today?
Sorry, you said that it could have aborted the transaction, but if it did, that it will never receive the commit.
You mean in response to the last question?
Yeah.
Yeah, the question was like, why does he have to record on stable storage what it decided to do? And the answer is that when B comes up, it needs to know whether it actually agreed to commit, or agreed to abort. And if it doesn't write anything, it doesn't know to what it agreed.
Because it could have
Right.
aborted after.
Yep.
Yeah.
Okay, I need to know that to know what to do in the recovery stage. I see.
Yes, exactly.
It also needs to record what it does, because if it like aborts, but the message never gets to the coordinator, it needs to resend the same message, right?
Yeah. Well, it needs to record that it actually aborted that transaction ID. So when the coordinator asks, what did you do? That it actually responds with a no.
Got it. Thank you.
Thank you.
You're welcome.
Thank you.
Okay, see you all next week.